Dear students, welcome to another day's lecture in Elements of Machine Design. Today we are going to see the design of keys. First, let us understand what is a key. You see, if there is a pulley and it is mounted on a shaft, when a shaft is rotating, the pulley should always rotate. You see, so if the shaft only is rotating, then the torque of the shaft is not being transmitted to the pulley. So positively, whenever the shaft rotates, if it turns through 180 degrees, the pulley also should turn through 180 degrees. So there should not be any slippage or anything like that. So therefore, to ensure that there is no relative motion between these two, shaft and the pulley or the hub, you say, what we do is we use a thing called as key. So key, what is a key? Key is a piece of mild steel. Normally this will be softer material compared to the pulley or the shaft, because this is designed to fail. That means if any in the assembly should fail, first should fail key, because it is a smaller piece, it is less costly to make. Okay, a key is a piece of mild steel. It is inserted between the shaft and the hub or boss of the pulley. You see, pulley is the total round, the pulley, and it may be having arms. At the center, there will be another, solid lump, and a hole for the shaft. So this solid lump, we can call it as hub or boss. Okay, so between the shaft and the hub, it is inserted between them. And why? To connect these together in order to prevent relative motion between them. This is, it prevents relative motion. That means what? If shaft is rotating through 2 revolutions, the hub also should rotate through 2 revolutions. If it is like that, then there is no relative motion. If shaft is more, rotating and the hub is stationary, or shaft is rotating 2 revolution, hub is rotating only 1 revolution, that means there is relative motion between them. So this is the definition of the key. Okay, it is always inserted parallel to the axis of the key. This is parallel to the axis of the key. However, the axis is and the axis of the key, both are parallel. They are used for temporary fastening. Sometimes they may be asking, is it permanent fastening or temporary fastening? It comes under temporary fastening, and it is subjected to crushing stress and shearing stress. We will see these things when we come to design of the keys. Crushing stress and shearing stress only, this key will be subjected. See, you can understand, you can see here that there is no bending stress, there is no tensile stress involved here. Okay, keyway is as keyway. See, key is one thing. Where key sits, that is called as keyway. Keyway is a slot or a recess in the shaft and hub of the pulley to accommodate a key. Okay, uh, we'll see the pictures also of it. Okay, types of keys, there are number of types of keys: sunk key, saddle key, tangent key, round key, splines, key with or without jib head, like that. Okay, then let us see the sunk key, which is the, important from our point of view, because this is the thing we are going to design. Other keys we are not going to design. Just the design of the sunk key we'll be seeing. See, the word sunk, from sunk means what? You see, it is comes from the word sink, sunk. Sink means dubna. डूबना, डूबा हुआ, डुबाया गया. हाँ, what? I don't know. Okay, sunk means डूबा हुआ. Okay, so that means what? ये जो है ना, इसका आधा आधा की जो है वो शाफ्ट में डूबा रहता है, इसलिए इसका नाम डूबा हुआ की है, sunk की. The keys are inserted half in the keyway of the shaft and half in the keyway of the hub. So in the sunk key also there are further different types. Rectangular sunk key. You see, if you cut the key across, it will be a rectangular sunk key, square sunk key, parallel sunk key, jib headed key, and other things. You see, now I want you to see, a video, and then we will further proceed. Some people call keyways as key seats. So now keys and key seats. We will see some pictures of these things. You see here. See, actually, the function is written. It is to lock shafts to hubs. Hub means it may be hub of the gear, it may be hub of the wheels, or it may be hub of the flywheels, or pulleys, or whatever. Okay, to lock means what? To when the shaft is rotating, along with that pulley should always rotate. It should rotate positively. Okay, for that purpose there are several types. You see, you can see here, you can see a square key, a rectangular key, you know. Yeah, let us see what are they. A square key, a rectangular key, a Pratt and Whitney key, maybe it is rounded here, on either side. Then Woodruff key, half moon, then tapered key. Okay, these are the different types. Then how they are assembled? You see, this is called key seat or keyway, and that is the key. See how it is cut, how the keyway is cut. Keyway means keys. See, for the milling cutter you can cut. So therefore when you cut like this, what happens is only this much portion you can use, then this much portion you cannot use, because this comes because of the curvature of the milling cutter. Okay, and here, it is assembled like this, half inside and half side. This is specially for the sunk key. Okay, and the okay. Okay, types of keys, different types of keys: sunk key, saddle key, tangent keys, round keys, splines, and Kennedy keys. Yeah, sunk keys are further classified as rectangular sunk key, square sunk key, parallel sunk key, jib head sunk key, feather sunk key, and woodruff sunk key. Saddle keys are further classified as flat saddle key and hollow saddle key. Let us see how they one by one how they are. Sunk key. Sunk key is like this. Half goes into the shaft, half goes into the hub. Okay, and in the side view it is seen like this here. And rectangular sunk key, its cross section, if you see, it is like a rectangle. Okay, width W and h height. Width is greater than the height. Then square sunk key is one which has width and height are equal. Width and height both are equal. W and h are equal. W is equal to h. Okay, then parallel sunk key. Parallel sunk key is, it's also rectangular, but it is parallel. See, that means what? There is no taper. Okay, it can be also rectangular or shaft. Why these keys are used? Where when the hub has to move. You see, this is the keyway, this is the hub, this is the jib headed key. Jib headed key, it has a head. It helps in removal of the key. Okay, then feather keys. Feather keys are like this. Parallel key, either to the shaft or the hub they will be fixed. Uh, it will allow the movement, relative movement like this. Okay, and then woodruff sunk key. Woodruff sunk key is a disc like this segment. It is fit like this. See, the keyway also is not. It is a part of a segment. Uh, Similarly, it will sit, especially in automobiles and in tapered shafts. These things are used. It will permit a little bit of you know movement. Uh, these are the saddle keys. Saddle key, there is no keyway on the shaft. You are seeing no keyway. Okay, you see only on the hub keyway will be there. See, in the because of the friction only this shaft moves. Therefore, okay, this is a flat saddle key. You can see flat saddle key. It is flat here, and here no, the shaft is little made flat, not a cut a keyway, but it is flat. Okay, it is used for comparatively lighter weights because only because of friction it should work. Otherwise, sometimes it may move. And there is another saddle key which is called hollow saddle key. It is cut a little like this, so there is no need of making flat on the shaft. It is sitting like this. Then tangent keys. These are tangent keys. See, there is a taper like this. They are fixed at right angles like this, here and here. Each key has it fits like this, and they has taper 1 to 100, so that this can be used either clockwise direction or anti-clockwise. Both side rotation of the shaft is there. Then this type of tangent keys can be used. Then round key, this figure is wrong. This is a wrong figure. You see, this has a keyway here, and there this is inserted. You see, like that it will be. It's a round key. In round key, there is no taper. And these are splines on the key, on the shaft itself, are cut. Okay, this is integral part. This is spline. Similarly, in the here, no, there will be mating recesses for spline. Okay, it will be used. And these are Kennedy keys. Kennedy keys are square keys. Square keys like tangent keys only, but tangent keys are having taper. Here, square keys, it's like this. Okay, so these are the different types of sunk keys. In sunk keys, if the cross section is rectangle, it is rectangular sunk key. If the cross section is square, it is square sunk key. If there is no taper, it will be parallel sunk key. Again, parallel sunk key can be rectangular or square. And then jib headed key. We will see what these things are. Okay. Now, first come to the rectangular sunk key. Rectangular sunk key, you see, this is the shaft and this is the key. The length of the key is parallel to the shaft. That's what we said earlier. It is mounted in such a way that the length of the key is parallel to the axis. Okay, and it is inserted at the periphery. Half of it is inside the shaft and half will be outside. That means inside the hub. You see, the hub is not shown in the figure here. In the side view, in the side view you can see the cross section. The width is W, the height is T. This is the length. And there is a taper. You see, taper, how much is there? Taper is 1 in 100. That means what? If you go along the length 100 mm, 1 mm will reduce. Again another 100 mm, 1 mm will reduce. If the length is 200 mm, then if this side it is 10, this side it will come to 8. That is the meaning. Okay, rectangular sunk key is shown in figure. The various proportions are. Proportions means what? Now we have W, this one. W is normally taken as D by 4. D is the diameter of the shaft, D by 4, and thickness is taken as D by 6. See, these are the things, that readily, empirical relations you can use readily. Okay, so W is D by 4. This is quarter of the diameter, and thickness is lesser, that is D by 6. So 1/6 of the diameter. Okay, and the taper is 1 in 100. You see, you compare the taper of quarter in quarter joint, that is 1 in 24 or 1 in 48. Okay, that means that is more taper. This is a less taper. Only in 100 mm one is reducing. There every 24 one is reducing, or in every 48 one is reducing. Okay, that is the meaning. Here taper is less. Key quarter has more taper. Okay, now come to the sunk taper key. Square sunk key. Square sunk key, the name itself says it is a square. Square means, it is not a rectangular cross section like this. It will be both same. W and T, they will be equal. So if it is a W by T, then you have to take this proportion, both D by 4. Then parallel sunk key. Parallel sunk key, the word parallel itself shows that there is no taper here. The parallel sunk key may be rectangular or square with taperless edge. The taperless means no taper edge. There is no taper here. Then you see, what for this taper is being provided. You see, if you on this, if you mount a pulley and if you hit it, on one side with the hammer, what it goes and becomes a tight joint. See, there is no relative motion okay, anyway, Kiwi is preventing relative rotary motion, but because of the taper, relative axial movement also it is preventing. That's why this taper is provided. Okay, but in some cases what happens is, on this shaft sometimes the pulley should go this side and that side. Axial movement of the pulley is needed. In such cases, this parallel sunk keys can be used. The parallel sunk keys are used where it is required to slide the gears, like whenever we are applying the gears, if you drive a motorcycle, a car, that we change gears. When we are changing gears, it is necessary for the gears to be slidey. Okay, so sliding of the gears, pulleys and other mating surfaces, if they are there on the shafts, so then parallel sunk keys can be used. Then another sunk key is jib headed key. It is just like the sunk key, only that there is a head which is called as jib head. This jib head, it is a rectangular sunk key with head on one end, and it is known as jib head. The key, this key can be easily removed. You see, because there is a head, you can just put some wire around the head and just pull it and it will come. Otherwise, an ordinary sunk key, what for dismantling, you will need some something like some metal piece or metal rod or something, and then you should hit it slowly with the hammer, and that's how it will come out. Okay, this means you can just tie a wire about this head, and you can remove it. You see, you can see the proportions. This is W and this is T and this is the length, but here there is some taper and the angle is 45 degree. This height of the jib head is 1.75 times of the thickness, and this is 1.5 times of the thickness. Okay, this much. Okay, anyway, we are not going to design this, so need not remember these proportions also. Okay, the other proportions, the width. Okay, this is the same thing, that what width, what is W here, this W, but there how much W did we take? There W D by 4. You see, this proportion is wrong. We have nothing to do with this. This is actually T. Okay, leave it. Don't worry about this. You just know how the shape of the jib-headed key is. Okay. Now the functions of the sunk key. What does sunk key do? It transmits the torque or the power between the shaft and the hub by shearing resistance of key of two mating elements. Okay. See, this is the important. The torque will be transmitted whenever a shaft is rotating, the pulley should rotate. See, if it doesn't rotate, what happens? Suppose the shaft diameter is smaller than the inside diameter of the hub. Then what? It doesn't rotate. So to ensure, if there is a clearance there, it won't rotate. So to ensure that it every time rotates, positively rotates, what we do? We insert the key. Okay, so it transmits torque. Or torque means what? Torque and power they are proportional things. So torque or power, it is transmitting from the shaft to the pulley or the hub of the pulley. How? By shearing resistance, because that is what it is trying to sacrifice. If it doesn't move, then it will shear off in the middle. It prevents relative motion between the shaft and the hub and join the machine element like shaft and gear. Okay, because hub is part of the central part of the gear or pulley. That's why it prevents relative motion between the shaft. Relative, see that this is not the important thing. Okay, it is, it comes with this. If torque is being transmitted, relative motion is being prevented. So both things are being done. Now let us see about the design of sunk key. Before that, I want to see about different types of keys and other things. You see this video. Yes, sorry, we have already seen that video before. Okay, continuing with the design of the sunk key. You see, design of the sunk key. See, your sometimes questions can be like this: what are the different types of failure considered while designing the rectangular key? Write strength equations. Okay, that is the meaning. That is the question. Okay, now let us see. You see, while tightening the straight key, or in a taper key. Straight key means he wanted to say parallel key, or in a taper key, these produce compressive stress. What statements they make? Okay, anyway, second is force due to torque transmitted by the shaft. This produces shearing and crushing stress in the key. See, these are the two things that come. You see, shearing stress and crushing stress. See, let us see. You see, T be the torque being transmitted in Newton millimeters, and F is the tangential force. Here, this new term F is coming. This is the tangential force. Tangential force means, you see, I will show you in a figure here. You see, if this is rotating and transmitting torque, okay, and this diameter is D, okay, you see, that means what? You see, at the periphery of the shaft, we can assume that this F is there. This F, that is the tangential force. You see, where from this F is coming? F is coming because of the torque. So is there relation between the torque and F? Yes. What? This is acting on the periphery. So the periphery force into the radius, that means D by 2. Okay, this is Newton, D by 2 is millimeter, Newton millimeter, torque is Newton millimeter. So F into D by 2 will be T, torque. See, that is what is this F. This is the tangential force. And the D is the diameter of the shaft, L is the length of the key, W is width of the key, and T is the thickness of the key. Okay, now see, you see, suppose this shaft is rotating. Okay, and the hub is there. In the hub and shaft, this key is sitting. Okay, suppose shaft is rotating and the hub doesn't rotate. What will happen? But for preventing that, only this key is there. But key also has certain strength. Beyond that strength, if this rotates, what will happen? It will shear here. I will show you one video here. If you apply the force, it will shear like that. That is a shearing failure. Did you see that? Okay. So this shears in the middle like this. So let us see what is the strength equation. See, the shearing stress, the direct shear, tau you can use, or tau D. Okay, that is shearing force upon resisting area. That means what? Shearing force is the tangential force F, and resisting area is, you see, it is breaking here. This is the area. This is W and this is L. W into L will be the resisting area. So, and torque. Torque is what in terms of the tangential force? Tangential force into D by 2 will be torque. So what is F? We can rearrange this like torque upon D by 2. Okay. Then this F you substitute here. So if you substitute, tau is equal to T by D by 2 upon W into L. This one here. So then you get an equation. Torque is equal to W into L into tau into D by 2. This is the equation for the torque. This is the equation for the torque in shearing. Okay, and now there is something crushing also involved. Crushing. Let us see if I can show you another video. Okay, now you see here. Now see here again you have this assembly, and then now if it is rotating, see if this is rotating, what will happen is, you see here, here it is crushing. This is crushing. You can see half of it is crushing. Okay, that means this surface may damage. Okay, if you rotate in the opposite direction, here half of it is getting crushed. Okay, or here opposite, a half of it, you see, like that. Okay, so crushing stress, you see, we don't call it compressive stress. You see, compressive is a bodily stress, and crushing is surface stress. This is only on the surface, it will be failing, so it is crushing stress. Crushing stress is, we have crushing stress sigma cr should be compressive stress, compressive force, or whatever the tangential force because of which it is doing upon the resisting area. Now the tangential force is F, and resisting area, it is half of it. Half of it is being getting crushed. Half means what? In this figure, shall we see in this figure? See, where is it getting crushed? You see, this upper portion of it. See, this height is T. So this is T by 2 and length is L throughout the length. So T by 2 into L will be the area. So the area in case of crushing will be T by 2 into L. Okay, or L into T by 2. So you substitute F relation is T into D by 2 and this one. So you will get another equation. See, this is sigma C. Why sigma C? Sigma C means sigma C are crushing. Okay, crushing stress is equal to, okay, T upon area, F upon area. F is T into D by T upon D by 2 upon L into T by 2. Okay, if you simplify this, you will get another equation. T is equal to L into T by 2 into D by 2 into sigma C. See, this is the area in crushing, and this D by 2 into sigma C will be there. In this equation, this is the area in shearing, W into R, tau into D by 2. Okay, these are the two equations important. Okay, in case of design of key. These are the only two equations you'll have to remember. Okay, you'll have to remember the equation for F also, but the important things is torque in case of shearing. What relation is there? Torque in case of crushing, what relation is there? These are the two things, two equations you should know. Okay, if you know that, you can find these things. Okay, see, now let us see what is the effect of keyway on the effect of keyway on the shaft. You see, if you are cutting something, what if you are that means what, you are removing some material. Keyway you are cutting, that means you are removing some material. Some material is removed means area is reduced. Area is reduced means stress increases. That is the meaning. So when the keyways are cut on the shafts, material is removed at the periphery, at the skin, thereby weakening the cross section of the shaft. Cross section is not weakened. Cross section is reduced, but the strength is weakened, or the torque carrying capacity is reduced. Secondly, the stress concentration effect is also serious at the cross section of the keyways. You see, any sharp corner is there, stress concentration comes into effect. Okay, that means what, if a crack initiates, it can initiate in that sharp corner. So this causes the shaft to become torsionally weak. So these are two reasons. One is the area is reduced. Second is because of the sharp corners, stress concentration is more. Because of this, shaft becomes torsionally weak. Okay, so we have to therefore compensate for this weakness by increasing the diameter of the shaft. So if it is failing, then what? See, we have used formulae, and we have arrived at a diameter in shaft design, and afterwards now we are reducing the diameter, means what? So to compensate that, you have to increase the diameter. Okay, so that your keyway can be cut. Okay, otherwise no, see, ultimately the minimum area of cross section should be there for resisting the torque, so that the shaft won't fail, should be there. So therefore what happens is you have to compensate it. Okay. Okay, so experiments have already been carried out on the shafts. So many people who are doing research and other things, they'll be doing so many experiments with keyways, without keyways for the same diameter. It has been proved that the ratio of torsional stress of the shaft and uh, yeah, and the keyways without the keyways for the same sized shaft may be expressed by some experimental relation, which was derived by this person H. F. Moore. Okay, the weakening effect E is equal to, that is shaft strength factor. E is this relation. Okay, see, and then if the shaft is too long for sliding keyway, then KO. Okay, see, we need not bother about all these things. Only that you remember, because of the reduction in area and because of the stress concentration at the sharp corners of the keyway, then the torque carrying capacity is reduced. And here they have made a statement. No, no. This value also of no, yes. Okay, only that much you remember. Okay, now let us come to some problems. See, design a rectangular key to be used for a shaft diameter 50. Diameter of the shaft is given directly. Both are having the same material. Both are means what? Shaft as well as key. Okay, take shear stress, permissible shear stress 42 NPa and sigma c is 70 MPa. So now we have now we have this torque equation for the shaft. T is equal to pi by 16 tau d cube. From this, because the diameter is given here, so shear stress is given, torque is not given, so therefore you find out what is the torque. Once you find out the torque, what are you doing? Design a rectangular key. You see, the torque finding also is not necessary. If you just have that, T is equal to d by 6 is 8.33, and W is equal to D by 4. I don't know why that person has not written here, or did I miss something? Okay, anyway, so this is 8.33. 8.33 should be rounded. Okay, and W. Okay, now, yeah, the same thing here also, sir. Okay, see, T is equal to 8.33. Now, crushing failure. Crushing failure, you have two formulae. So this is one formula for crushing failure. Crushing failure is T is equal to L into T by 2 upon sigma Ck. Sigma Ck or Cr, whatever, this is crushing stress, into D by 2. T, you have found out. L, you have found out. T, you have found out here. L you don't know. T, you have found out. So for substitute everything, you get L. L is 141.42. You can round it to 142. Okay, this is the length of the key. We are designing the key means what? You are finding what is length, what is width, and what is the thickness. Okay, then considering of the shearing of the key, shearing also we are having a formula. That formula is this one: T is equal to L into W into tau into D by 2. Okay, here you substitute now L also you have got. From this you can find out W. You see, actually it is not done like this. See, first what you can do is you have to uh, find out you have to find out T and W. Okay, by those relation T by W, what relation are there? This is the T's relation, D by 2, and W is D by 4. These two you find out. After finding out, what you can do is, from one of the equations you can find out what is the length. Okay, like here we have found out. After finding that, from the other relation you can find the induced shear stress, whether with this is within the permissible limit or not. Okay, that is simple. Okay, now sometimes, many times, a question is asked. You see here the question is missing. I don't know how I did this. Okay, they say the question is important question. So many times asked in the question. You see, the question is, prove that for a square key, you see, square key equally strong in shearing and crushing, the compressive strength is 2 times of the uh, shearing strength. Prove that. That is the question. Okay, so we have two equations here. T is equal to W into L into tau upon D by 2, and T is equal to L into T by 2 into D by 2 into sigma C. These are the two equations. Okay, and now suppose it is equally strong, means equal torque carrying capacity. Equal torque carrying capacity means this T are same. So you equate these two because they are equally strong in shearing and crushing. Okay, so equate it. So now whatever is common you cut it off, and because it is square key, W is equal to T, so here everything you cut off. Cut. D by 2 can be cut, D by 2 can be cut, this L can be cut, L can be cut, this W and this T is same, so this can be cut. What is remaining is sigma tau is equal to sigma C by 2. This you will find out. That means what? Sigma C is 2 times of tau. So this is how you can prove it. Normally it is asked maybe so for 4 marks or something, or it can be 2-3 marks now, because your question paper is only for 70 marks. Okay, and so 70 marks, and you have to answer in 4 hours. This question paper will be in 4, exam paper will be for 4 hours, so you will have a lot of time. Okay, sigma C is 2 times of tau D. This is how you have to prove. What is the question? You see, question is, prove that the square key, which is equally strong in shearing and crushing, has compressive stress 2 times, or crushing stress 2 times of the shearing strength. Okay, that's what you have to prove. Okay, now another problem here. A pulley is keyed to a shaft of diameter 100 mm by means of key of 20 mm width. Key width is 20 mm. 20 mm means 2 centimeters. It's a big key. And 150 mm is the length. Okay, and this is 100 is what? Shaft diameter. Okay, the allowable shear stress is 40. Crushing stress is 100 Newton per mm square. The shaft is running at 250 RPM. N is given. Find the power transmission capacity. Now, power carrying capacity means P you had to find. Okay, and the thickness of the key also. Thickness is not given because only the length is given and the width is given. Okay, now let us see. Now what you have to do, this is all the data that you are having. Okay, now considering the shearing failure formula you are having two formulae. One is for shearing failure, one is for crushing failure. Shearing failure, from the shearing failure formula, because it is T is not there. See, thickness is not there, so which formula you will use? The formula where thickness is not there. Thickness is there in crushing equation, but shearing equation you are not having the thickness, so use the shearing equation. So W and so W is 20, L is 150, tau is 40, and D by 2, D is 100, and now everything is known. So torque carrying capacity, and you found out. Once torque carrying capacity is found out, power carrying capacity, power transmission capacity also you can find out. How will you find out this? Power carrying capacity you can find out by this equation, power equation, 2 by 10 upon 60. So everything you can find out. And now the thickness of the key, you are having the other equation, shearing equation you have used here, and the crushing equation you are having. From that you substitute everything, you will find out what is T. Okay, And one more thing, sometimes no people will be asking, there is a taper in the key, no? So one side is flat, only one side is taper, like like in the case of quarter also, quarter also taper on one side, here also taper on one side. See that the flat one, that means where told not taper is not there, that flat one is in the shaft, and where taper is there will be in the hub. Okay, you remember, so the keyway in the hub should be tapered. Sometimes that can be asked as an interview question or viva's question. So where the taper, which keyway is tapered, so the hub keyway is tapered. Okay. Okay, then today that's all. Thank you, we'll stop here.